Good afternoon to you all. So we continue in the series of our lectures on automata theory and computability. Of course, last week we concluded our teaching on the introduction to models, and previously we had looked at introduction to the preliminaries, like what you need to maybe refresh your memory on. We looked at the concept of uh, preposition. We moved to compound preposition. We looked at the truth values of this preposition. Then we looked at certain characteristics of a preposition, the synergism, the tautology, uh, the associative law, and several other things. We went further to look at basic definition to lay the foundation for um, the course, as it were. We looked at symbols, we looked at strings, we looked at concatenation, we looked at the clean closure, we looked at the clean star, and we looked at how some of these um, notation can be expanded. We also learned the concept of uh, empty set or empty string, which is represented by either lambda and file, depending on the textbook that you are working with. Now, all of these is to set up the foundation for this course and for what we are going to be seeing in the coming weeks. Now, of course, for you to be introduced to a new concept or a new topic, it takes a lot of time to build your capacity in that area. And you also saw that when we started the concept of modeling or introduction to modeling, types of modeling, we said that for you to be able to abstract from the complex reality of life to a particular area or a particular formalism, you must have certain understanding in that area of that you're abstracting to, so that you'll be able to think in that formalism. Now we looked at an example. We looked at some examples where we looked at number of chickens and goats, no, chickens and rabbits. We modeled them using different concepts, their legs, and also the total number that they seem to have, right? So these are the things that you have to get used to. So for you to abstract from total number of goods, total number of legs, total number of animals in the pen, you must be able to understand certain formalism in simultaneous equation or mathematical equation. Then we also looked at the apple that was dropping from a tree of height h. Now we looked at, okay, how can we in a way calculate the height of the is it the height from where the apple dropped. Of course, you must have some understanding on the formalism. Must have some understanding on the formalism of physics. Not only that, you must have certain idea on material particles or maybe laws of motion, such that you'll be able to look at analog signals that you have to process, and you should be able to also go and maybe model or abstract to that formalism, then solve the relationship to be able to get out what you want. Now, all of these are preparing what we needed to learn in automata theory. Now, we also concluded last week that we have certain types of model. We have mathematical, we have a physical model. We looked at the characteristics of physical model, disadvantages. We looked at formal models, which are mathematical in representation. Then we looked at computational models, right? Which a typical example is the finite state automata. we argue that finite state automata means that it has a beginning and it has an end. So when something is finite, it has a starting state and an ending state, right? And also the states, there's um, maybe a provision for you to move from one state to another upon the receipt of an input symbol, right? So these are the things we have built up over a period of time. And we concluded by looking at a typical example of maybe a very little, a system or a finite automaton with a very limited memory. And also we argued on what some of these models or some of these automaton, what they can do. So also note that when we say automata is the plural, that means several automaton, right? So automata and automaton will be used interchangeably. All right. So we go back again just to have a refresher of what we did last week on finite state automata. So the theory of computation begins with a question on maybe what you are working on, and of course, but these real computers are quite complicated, right? So much so to allow us to set up a manageable mathematical theory of them directly. So if you have maybe one aspect of the computer or several aspects of the computer and you need to model them, it will take several mathematical equations to represent it. It becomes very complex. So what do? You can abstract, at least strip the computer of certain areas, right, that you want to model, then go deep into that area that you want to model, right? So instead, we use an idealized computer called computational model. So computational models are what? Idealized computer. Now, as with any other model in science, a computational model may be accurate in some ways, but perhaps not in every other ways, right? So thus, we use several different computational models depending, now look at that, depending on the features we want to focus on. Now, oftentimes, like this in past years, I always tell maybe automata students that look, don't introduce your idea into the model you are told to model, or maybe a situation you are told to model. Don't bring in your own idea. Look at the definition, look at the situation described, look at the aspect of the computer you are told to model. Of course, you may have ideas of other areas and how they interact with that aspect you are modeling. But if their interaction is not mentioned, please ignore it. Just model what you are told to model and move on. Thus, we'll use several different computational models depending on the features we want to focus on. So we begin with the simplest model, which is called the finite state machine or finite automaton, right? So when you say automaton, singular, when you say automata, it's a plural. So what is the finite automata? So what are finite automata? So finite automata are good models for computers with an extremely limited amount of what? Memory, right? What aspect are you modeling? Memory. And what aspect of that memory are you looking at? Limited memory. So you are not looking at sufficient enough memory to do everything. It's just little things. And what can a little or finite memory like that do? Several things. Then you can pick one thing that it can work with or that it can do and model it. And that's why we're looking at the issue of the sliding door at a supermarket, or we give an example of the DLI. So in fact, we interact with such computers all the time as they lie at the heart of various electromechanical devices. So the controller for an automatic door is one example of such device. Now, often found at supermarket entrances and exits. So automatic door swings open when sensing that a person is approaching. So you see, we're now describing to you the operation of the automatic door. We say the first thing you need is that it will swing open when sensing that a person is approaching. That means it must have a sensor, it must have a state that it was before sensing that somebody was coming. And when somebody gets on the sensor pad, it will go to another state. So if you look at that, it was in a closed state. Sensing that somebody was coming, it received an input through the sensor and it changed the state of the door from closed to what? Open. Now, once the person gets in, the door senses that nobody is on the pad again. What does it do? It shuts the door. So we are describing the operation of that analog system, and we intend to model it using a computational model that can be represented using a finite state automata. So another pad is located to the rear of the door so that the controller can hold the door open long enough. You see, there's something introduced again to this door. It is not just in front when maybe at the entrance where when you are coming from outside, you step on it, opens. No, it's also at the back, that's in the supermarket itself, such that by the time somebody is trying to exit after shopping, the door can still get opened. So its operation now becomes a bit complex again, right? That means it will monitor the outside part, it will monitor the inside part to make sure that it operates optimally. So a little memory, monitoring inside activities, and also monitoring the outside activities, just to make sure that the safety is ensured with that door. So that the door does not strike somebody standing behind it as it opens. This configuration is shown. Of course, we looked at this last week. So the controller is either of two states, open or closed. So for any automaton, it must have certain states, right? It must have different states that it can move from one state to the other. Just like this morning when you woke up, you were lying down on your bed. That means you were in the lying state. As soon as your alarm comes up or somebody disturbs and you start coming back to life, you stand up from your bed. That means from state of lying down to the state of motion, you started moving afterwards, right? So that means your initial state, the state you were before any input gets to you, was what? The initial state. The initial state for you sleeping is your initial state. Then you receive an input symbol, maybe alarm, or maybe when somebody just disturbs you and you decided to stand up. So the input symbol is that alarm or somebody disturbing you. Then when somebody disturbs you, you come from sleep to a state of awareness. So that means your state changed from one sleeping state to two awareness state, three to maybe standing up and doing your morning chores, right? That is what the automata does. It represents the movement from one state to another. We're going to be defining some of these formally. I just want you to have at least a pre-knowledge of what we want to be assessing once we are modeling using finite state automaton. So for this door, this swing open and close door, so the controller is on either side of oh, are you seeing the what I'm displaying?
Yes, sir.
Oh,
Yes, sir.
great. So you have sensors placed on the front pad, sensors placed on the rear pad, and this is our door, right? So the door is expected to swing open or swing closed. Okay. So what does it mean? It means that the door is in a particular state here, and that means, so let's look at what this is saying. Say the controller is in either two states. Is either it is opened or it is closed. So we are interested in states in finite state automata for our modeling. So this door can either be what? Opened or it can be closed. Now, representing the corresponding conditions of the door. Now, shown in the figure following, and the following figures, there are 4 possible inputs. So there must be something to trigger the door to move from one state to the other, just as you were lying down, sleeping. If your alarm does not go off, and let's say it keeps raining and the whole place is still dark, there's no noise, there's a possibility that you can sleep till 12 noon, right? But if something happens, maybe your alarm comes on, it moves you from one state, the state of sleeping, to a state of being awake, right? So you must have a state or several states that you have. Maybe if you model your day's activities, there are several things that can happen during the day, and there are several states, and there must be several triggers that can make you go from places to places. Now, let's assume that this were to be a physical class. You must leave your hostel because what? There is a lecture. So what happens? You either take a cab or a bus, or you trek from your hostel to the E303 where the lecture, or E304 where the lecture is supposed to hold, right? So what happened? The lecture was the trigger, moved you from the state of your hostel to a new state, which is lecture hall. Now, you see, we just wanted to model your activity for today. There are several things that you can model. You can decide to be coming from your hostel and you decide to visit a cafeteria and eat first. But because of the urgency, you want to quickly get to your hostel, to the lecture, so that you secure a space. We ignore every other thing. Oh, you may see a new car just raving along the street, and you too, you'll be shaking your head and thinking, oh, I wish I can buy this car. We are not interested in that aspect of your day. We just told you model your activities from waking up to coming to getting to lecture hall. That's all. So that somebody slapped you, we are not interested. That the conductor or the bus cab driver didn't give you change, we are not interested. All we are interested is in that you left your hostel, you took a cab, you got to the lecture hall. That's all. So you see, there are other complex things that happened in you moving from your hostel to the, but because we have just told you, model your movement from where? The hostel to where? The lecture. That's all we are interested in. However, you are going to be learning later when it becomes a bit, at least when you are grounded a bit, there are what we call contingencies. That, oh, if for instance now you are coming and maybe your cab just decides to break down on the way, you see, in the first instance, I'm not interested in, maybe your car broke down, or maybe it was raining cat and dog. I'm not interested. Just leave your hostel, get a cab, get to the lecture. That's all I'm interested in seeing in your models. But there are some contingencies that, oh, what about if you are coming and the car breaks down? You are supposed to maybe jump out of that car, look for another cab, and start coming. So if that happens in the first model, we are not interested. But in the second model, you will introduce that contingency. If you are coming and your car breaks down, take another cab. That's a loop. Oh, if the car breaks down in front of, let's say, Jaja, or let's say where is CITS, and it's close by to E33, you can either take a cab or start running towards the lecture, right? That's another contingency. Instead of taking another cab, you can say run to the lecture. Now, let's assume that whilst you were coming, all of a sudden you saw one cow that just got lost and it was charging and running. Nobody will tell you that you are supposed to run away to save your life. So you say if you see any dangerous object, that's another contingency. Avoid that dangerous object and look for a safer place to get to the lecture. You see, those are contingencies that can happen during your modeling. However, we want to always strip models of any cumbersome details. Just delete the list of representation. That is what we want to use to represent our model for every situation. And that's what we want to use for this door that we're looking at. You see, the door is either closed or open. Now, what happens when it was moving from open to close? And suddenly it sees that somebody is about coming. and it returns to the state it was before. We are not interested in that for now, but it's a possibility. If you go to DLI, for instance, you see the door closing. As soon as you notice that somebody's in front, it will just be it will not close completely. It will just open. So that means there's another state in between open and close, which is semi-close or semi-open, right? So that means that's four states. So depending on what you want to model, make sure that you keep it as simple as possible. So the input that you can have to change the state of this door from open to close is what? Front, which means that the person is standing on the front part. Then there's another input, which is rear, meaning that a person is standing on the part to the rear of the door. Then both, that means somebody is standing in front or at the back. Neither, nobody is in front or at the back. Now, the top view of that model is represented using this diagram here. So what does it mean? Now, we have already demystified the working of that door, of that supermarket door, to have what? Two states, closed and opened. So this is what you have represented, closed and open. Now, these are called what? States. This is a state. This is also a state. Now, follow gradually. Now, you have input symbols or inputs that will make it change from one state to the other, that will make it move from open to close or close to open, or even remain open or remain closed. So what happens? That means you are closed. Upon the receipt of an input symbol, rear. Now, what is the definition of rear? Means that somebody, meaning that a person is standing on the pad to the rear of the doorway. That's what rear means. Now let's interpret together. If the door is closed, right, and somebody is at the rear, what does this diagram say you should do? That means if you at the closed state and you receive an input symbol rear, it tells you that it should remain closed. Now, now look at both. It has another input symbol, both. What does it mean? Meaning that people are standing on both parts. What did he recommend? It says remain closed, right? It says remain closed when you receive both. When you receive neither, that means nobody's in front, nobody's at the back, and you are closed. You should remain closed. Now, let's consider the situation. If somebody is at the rear, and of course, we assume that this door opens to both, maybe one direction, probably. So if somebody is at the rear, don't open so that you don't slam the person off. If somebody is in front and the back, just wait. Maybe one of them will step back so that the door can open. Then if neither, that means nobody wants to enter or nobody wants to exit, then you remain closed. That is the input symbol for this state. However, once you are in closed states here and you see that somebody is in front of the door and wants to get in, that means front means that somebody is standing on the pad in front of the doorway. That means he wants to enter. So what happens? This door that was ab initio closed, we move from being closed to being open. So in this situation, we have left this place. We are no longer considering closed state again. So we are now in open state. Now, it now says that once you are in open state and you see that somebody is still in front, you remain open. So this arrow means remain open. Just a bit. Yeah, so this arrow is saying that you should remain at the same place. So you see, it's emanating from open, going back to open. That's what it means, right? Now, you say if you are opened and you find out that there's somebody at the rear of the door, then still remain open so that the person can get out. Now, if somebody is in front or at the back, still keep the door open so that the two of them can go in or go out. Now, If you are opened and you don't see anybody in front of the door or at the back of the door, what do you have? What do? You close the door so that the gas of the AC will remain intact. So that is a way of modeling generally. That is how we think about modeling. It is brain taxing, right? It's easy, at the same time it's complex, but there are certain formalism that you ought to have known before modeling, right? And it's also important that you are patient when you are anytime you want to model, and you also listen to the description of the problem you need to model. All right. So moving on. So this whole thing we have just explained is represented using a semi-truth table here. So let's think again in that direction. So you see, these are the states. And what are the states we have? We have the what? The closed states and the open states. So it now wants to tell us how can the door react to certain inputs once you are in a particular state. So these are the thinking states. So it says that if you are in a closed state, right? So you are in a closed state. Let me clean it again so that we have a better. So once you're in a closed state and there is nobody in, okay, and there's nobody in front or at the back of the door, you're in a closed state. What did he recommend? Remain closed. Now, once you are opened and there's nobody, neither again, there's nobody in front or the back, then close the door so that the gas will not waste. That is where the door will be. So if you want to draw this now, let's assume that this is the closed and the open. So let's represent by C and P. So let's interpret this. Let me clean it so that you'll be able to see. Okay, so it says, oh, cleaned everything here. So this is our closed state and this is our open state. It says here that you are in a closed state here. This is closed state. And you receive an input symbol, neither. Let's represent that by N. It says you should remain at what? Closed state. So you receive an input symbol, N. So let's put N. And you remain at closed state. Now, if you are in open state and you receive an input symbol, N, which is neither, what do? You remain closed. That's the first thing. That's the interpretation of this. Now, the second one, it says you receive an input symbol front. Let's represent that by F. If you are in the closed state, right, and you receive front, so you are in closed state and you receive front, it says you move towards open state. So this is front. It says you go towards open state. Then once you are still in the open state and you receive a front, that means somebody is here, you remain at where you receive maybe a front. You see, you are still using this same arrow, you remain open. So you move from close to open, but here you remain on open. So we have created this. Now the third one said you receive an input symbol rear and you are closed. You are closed. You receive rear as the input symbol, but the door was closed. So what do you say? It remained closed. So you put it as what? R, which is rear. You remain what? Closed. Now, once you are at open state, you receive an input symbol rear. What did it say? It says you remain open. So here you put your R again. Now we have done with this. Then it now says when you receive the input symbol both, you are at closed states. So you are here and you receive both. So B, it says you should remain closed so that you don't strike the person. You remain closed. But once the door is opened, right, and you received both, you keep the door sufficiently opened so that at least somebody will be able to come in. So you put a B. That is how you interpret computational model, especially when it comes to automata theory. Don't get worried. You at least, it's just an introduction. You get to understand it a lot better shortly when we go into a better example. So let's look at what the story behind this. Say the controller moves from state to state. Now start noting it. The controller moves from what? From state to state. Yeah, from state to state, depending on the input it receives. So these are inputs. All these are inputs. Then these are the states. So depending on the input you receive, you move to a new state. So when in the closed state and the door receives input neither or rear, it remains in the closed state, right? So this is it. It's in the closed state and it received the input symbol neither, it remains closed. When it received rear, it remains closed. When it received both, it remains closed. Now, in addition, if the input both is received, it stays closed because opening the door risks knocking somebody over on the rear part. Now, but if the input front is received, that means if you receive this front, it moves it moves to the open state once you are at the closed state and you receive front. That's so. But if the input front arrives, it moves to the open state. In the open state, if input front, rear, or both is received, it remains in open. Now, if input neither arrives, it returns to close. So depending on what you are told to model, you must be able to think critically to represent the maybe the situation you are told to model in computational terms. But there are certain things you must understand first before you start abstracting from the complexity of what you are told to model. So this is one of those things, and that's why I told you that when we're learning how to interpret those truth symbols to English, and that was the test you did last week when I told you to interpret what a particular diagram was in English. You should be able to convert symbols to spoken English, and you must also be able to convert spoken English to models or to symbols in that formalism for you to be able to think on them effectively. So these are the things when we're doing introduction as though we're wasting time. Those were the things we're trying to learn at that instance so that we'll be able to apply it here. Okay, so this is just what we have done. If this, then this, right? So if the door is open and it receives this, then it's closed. This is what we have just applied in this area. Okay, so moving on. So just pay very good attention. So for example, a controller might start in the closed state. So we are going deeper and deeper, and we are going to be sliding down very fast now. All the first four lectures we have done, we have been very slow learning new things. But now we're going to be applying those things and it will be very fast. We're going to be changing from from situation to situation at a very fast rate. So please, it's better you listen and assimilate as fast as you can. Now, for example, a controller might start in a closed state, right? That means they want to tell us where we should start from our modeling and receive the series of input signals. What are those input signals? Front, rear, neither, front, both, neither, rear, and neither. Now, remember, in our second lecture, we define what a string is. And we also define what concatenation means, and we also define what is an ith symbol, right? So if you look at this now, all of these are just symbols in a string. So if you represent them by letters, so this will be what? F, R, N, F, P, N, R, and N. So this is a string of inputs. Now, what is the total, or what is the modulus of this whole string string we want to pass through? How many symbols does it have? It has 1, 2, 3, 4, 5, 6, 7, 8. So the modulus of this equals what? 8 symbols. Now, don't get confused. I just took the front letters of each of these. That's what I did, just to represent them instead of writing them both. So what do you see here? These are just strings with what? Symbols. So each of these symbols is passed at every instance of time, one at a time, one at a time, one at a time. So look at the next statement. It then would go through the series of states, starting with closed, right? Now, look at the way it thinks now. Say, for example, a controller might start in a state closed. That means the state you meet yourself is closed, and it receives a series of input signal. So let's go back a bit. Here's that diagram. Yeah. So, okay, so it receives series of input symbol. The first thing it receives here is what? A symbol front. So you are at closed states, you receive an input symbol front. Where do you go? You go to state opened. So you see, you are in closed state, you receive this input symbol, the arrow telling us where, you go to what? Open state. The next one, you are now in a new state called open. You receive rear. Once you receive rear, you remain on open. The next one is what? Neither. Once there's nothing, you go back to what? Closed state. Then once you are in closed state, you receive front, you move to open. You receive both, you remain here. You receive neither, you close. You receive rear, you remain closed. You receive neither, you remain closed. So that means the door will remain closed at the end of the day. So look at what this series of thinking now did. He said so it then will go from what? The series of states from starting from close. It receives at front, it goes to open. Rear, it remained open. When there's neither, it goes to close. When you receive a front, you open. When people are on the two part, it remain closed. Remain opened. When there's neither, you close. Once you are the rear, you remain closed. Once there's nobody, you remain closed. That's what we have just traced in that diagram. So there's a need for you to be able to look at the diagram and also think from you receive inputs and you move to another state. So automata theory operates with receiving input symbol from a string, at least one symbol at a time from a string, and changing from one state to another. That's how it works. So the controller is a computer that has just a single bit of memory capable of recording which of the two states the controller is. So that's what we want to look at. A simple a single bit of memory that is capable of reporting the states of the door per time. Now, other common devices have controller with somewhat larger memory. In an elevator controller, a state may represent the floors, the floor the elevator is on, and the input might be the signal received from the button, right? So depending on which state you are, right? So this elevator is another complex representation of a computer. So the way we represent it will be quite different from what we have seen in that of close and open door, right? Okay. So moving on. So this computer might need several bits instead of just one bit to keep track of this information. So what will happen here? we need several automata to be able to represent the behavior of the lift, right? Okay, for instance, you go to any building, you press the button. Now, if the lift is on the 7th floor, you can't just enter. You have to wait until it travels. Maybe it's going to the 12th floor, then it comes back. Then maybe when it's going to the 12th floor, at the 12th floor, maybe the vice chancellor is waiting to enter, and maybe they are special guests. And you have pressed maybe on floor 2, and you have maybe 5, and you want to come down. The door will not open for you. Why? Because there's a constraint. Once the vice chancellor is in the elevator, it goes straight down, just as a form of security for her. However, if the vice chancellor is not there and it was just any other staff member, you could also join. Maybe when it's coming from the 12th floor and you're in the 5th floor, it opens. That's another rule. You must represent that movement with another condition. That, the elevator may be, the opening door may be at 12th floor, and you will say, okay, once you are in the 5th floor and it's coming, it must open for you to enter at 5th floor. But what about if other conditions exist? Maybe special people are in the elevator, it will not wait for you. It just goes straight down for the security of those people, you see? So you will need several automata to be able to process and represent such complex interaction. So the design of such devices require keeping the methodology and terminology of finite automata in mind. So there are certain things we now want to look at. I haven't looked at, how you move from state to state. There must be conditions attached to your moving from state to state, and there must be several representation and notation in that formalism for you to be able to think in that regards. So let's move forward a bit. So we are moving into deeper waters now. So finite automatons and their probability counterpart Markov chain are useful tools when we are attempting to recognize patterns in data. So these devices are used in speech processing and optical character recognition. So Markov chains have been used to model and predict price changes in financial markets, for those of you who are doing crypto. So we will now take a closer look at finite automaton from a mathematical perspective. So we develop a precise definition of a finite automaton, the terminologies for describing and manipulating finite automata, and the theoretical result that describes their power and also their limitation. So this is what we'll be looking at throughout this course. So that's why you're going to be looking at the power series too. Now, besides giving you a clear understanding of what finite automatons are and what they can and cannot do, this theoretical development will allow you to practice and become more comfortable with mathematical definitions, theorems, and proofs in a relatively simple setting. So there are certain complex notations that we are going to make you escape from. We're just going to try to get you out of those complex notation that you just look at, if we think of this in computational models, will it be easier for me to work on than for me to be using mathematical representation or physical representation? Oftentimes, I've seen students over the years, we teach you something in finite automata. You will go and start using mathematical theorems that was not recommended for you. So please be at least be warned on that. So let's dive deeper into finite state automata. So from all we have done so far, in all of this, can somebody tell us what you understand with what you are seeing on your screen? Can somebody interpret what we are seeing on this screen based on what you have learned before, from close to open, then the arrows and all that? Just raise up your hand if you want to attempt. All right, Aladetan to Tony Lola, Tony Loba. Yes.
Good afternoon, sir.
Yes, please.
Okay. So from what I'm saying, there are three states on the screen: Q1, Q2, and Q3.
Good.
The beginning arrow to Q1 means that Q1 is the start state.
Mm-hmm.
And then there's an alphabet here that uses 0 and 1 as the inputs.
Good.
So we start at Q1. If the input is 0, then the automaton will remain at state Q1. But if the
Good.
input is 1, then the automaton will move to state Q2.
Good.
Then at Q2, if the input is 1, the automaton will stay in Q2. If it's 0, it will move to Q3.
Good.
At Q3, if the input is 0 or if the input is 1, it will move back to Q2.
Good.
And lastly, Q2 is our accept state, meaning that if we stop at Q2, that string will be accepted, the string that stopped us at Q2.
Ah, okay. Thank you. You have done over syllabus. Yeah, I hope all of you understand or what he has explained. Yeah. Does anybody have any question on what he has explained so far? Just raise up your hand. Questions on what he has explained? All right. So let's move on. So from what you have learned so far, in what we have, at least where we are coming from, we have not done anything on this, so don't bother. But we have learned something on states, right? So we have three states, Q1, Q2, and Q3. Good, right? We have also learned that you remain at a state here once you receive an input symbol, then you make a transition when you have what? This input symbol 1, right? So this was open, close, open, rear, neither. It has been represented by what? Ones and zeros, right? And what I just want you to know that these are states which we have looked at. Then these are just movement from state to state or remain on these states. That's what we have learned so far. But there are certain things we need to learn again just to carry our knowledge from the simpler things we have learned to maybe to improve our knowledge a bit. Now, the way I teach is to move you from the lowest place first, move you a little bit about, just a little bit, then we remain there. Once I see that you've understood, we pull you up again so that we just jack you from nothing to something. Let's just build it gradually. Of course, it's going to be boring at times because there will be repetitions, there will be emphasis, there will be this, and some of you, you are bored, you are bored. But you may know it. Some people don't, they're even confused up to this point that you have been able to explain. So we know states, which are Q1, Q2, Q3. We have input symbols, which are what? Zeros and one. So let's now look at how this relates to what we have learned in the previous classes. So the figure above is called a state diagram. So in representing our finite state automata, we have what is called a state diagram. Then also what we call a state table. Now we have not gotten to state table now. That's another place we're going to jack ourselves up a bit. So of course, when we say the table above, the figure above, this is the figure we are referring to. So the figure above is called a state diagram with a name M1. Now it has three states labeled Q1, Q2, Q3. I hope you agree with that. Now it says that the start state Q1 is indicated by an arrow pointing at it from nowhere. So let's go back and look at it. So this is the new thing you are being introduced here. So you see this arrow pointing at it from nowhere indicates that this is the beginning state. This is where you must start, right? Just as we say, the door of the supermarket must be closed. There you now receive, maybe somebody's on the pad outside, it opens, right? It now start moving its transition. So that closed state is the initial state, right? So that's first. So you now understand what the initial state is all about. So this arrow coming from nowhere is indicating that Q1 is the initial state. Now, please note, is we are making it as simple as it is now. There can be other instances where there will be several arrows pointing at different nodes. So that means you can start your initial state from any of this angle that will support your thinking processes. So, but let's leave it as, I'm just giving it as heads up for you. Okay, so moving on, it says the start state Q1 is indicated by arrow pointing at it from nowhere. So please internalize that now because you are going to be seeing it a lot. And if I ask you to draw a finite state automata and you don't put the initial state, even if you get everything correctly, I'll give you 0. So you should start internalizing and imbibing some of these things now. That's what will form the part of your mastery of this representation or in this formalism. Now, the accept state Q2 is the one with a double circle, right? So if you look at this, you see this guy with a double circle, Q2 with a double circle, right? That is called the accept state. So what have we learned? We have learned of states, we have learned of initial states, and we have learned of accepting states, right? So we are trying to build up the properties to describe an automaton. Now, the arrow going from one state to another is called what? Transition. So you see this arrow moving from here to here, moving from here, 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 is called the transition and is often represented with what is known as the transition function. Now, when the automaton receives an input string, right? So these are what? Input string. So each of it represents what? A symbol. Now it processes that string and produces what? An output. It processes each of these string and produces an output. So the output is either in accept state or in the reject state. Now we consider only this yes or no type of output for now. You see, for now, to keep things very simple. So we are going to be getting to very complex systems at a later stage. Now the processing begins in M1's what? Start state. The start state what is the initial state. So what is the start state in this diagram here? What is the start state?
Q1. Q1.
Yeah.
Q1.
Yeah, that's correct. So it begins with the start state, which is Q1, right? Where is it? I'm coming. Okay, with the start state, which you have identified. So the start state can also be called the initial state. Now, the automaton, one automata, that's a singular automata, receives the symbols. So each of these are what? Symbols. So every element of a string is called a symbol. You see, we're defining that earlier. And you say, oh, well, what do we need this for? What's it now? You are needing it. And instead of me teaching you, we're just mentioning it for emphasis. Later, we'll not even come back. We'll not even talk about it again. We'll just say symbols, strings, accept or reject. All right. So after reading, okay, sorry. The automaton receives the symbols from the input string. So this combination is the input string. Individual is the symbol. One by one. From where? From the left to the right. So please pay close attention to this. It's important for you because if you don't get this foundational knowledge, all other things will look like film to you. So let's go back again to see just if you understand what I've said. Now look at this symbol or this diagram. We have learned of the what? The start state or the initial state. We have also looked at the states. We have looked at the accept state. Then we have looked at the transition. Then we now say that it takes in what? Input symbols, right? Each way left to right. So it processes this one first, this one next, this one next, this one next, this one next. So what happens if it has taken all the input symbols in the string? We will now conclude if it is accepted or rejected. This, what I've just explained is very, very important. All right. So, so when the automaton receives an input string such as this, it processes the strings and produces an output. The output is either accept or reject. Now, we'll consider only this yes. Okay, I think I've read this. So after reading each symbols, M1 moves from one state to another along the transition. that has that symbol as its label. Now, when it reads the last symbol, M1 produces its output. The output is accepted or is in the accept state if, can you mute yourself? So after reading each symbol, M1 moves from one state to the other along the transition that has that symbol as label. When it reads the last symbol, M1 produces its output. The output is accept, that means an accept state if M1 is now in an accept state. Now, in this diagram, what is our accept state?
Q2.
Good, Q2. So if after you have processed your input string and anything you process gets to this point and stays at Q2, then that string or those symbols is said to be accepted by that automaton. So that is thinking on the model. So if you now say, okay, if I want to make the door closed and I now passing through series of things, and let's assume that somebody maybe wants to waste your gas and decides to drop a stone on the pad outside. The door will remain open and you now be wondering, what's happening? What's happening? You don't see anybody, but the pad is sensing a weight. So what happens? That means that's a string that you have processed is rejected because the door should go back to the closed state after processing every entry and exit from the supermarket, and reject if it is not on what? Q2. So, oh, sorry. So I think I moved this one here just for us to be able to see. Now, for example, when we feed in input string 1101 to the machine M1 in the figure that we're showing, the processing proceeds as follows. So please, let's look at these processes together. Okay. Can you see this diagram here?
Yes, sir.
Yes, sir.
Okay. Okay, so let's watch what happens. So it says you are supposed to take in what? This string. Where do you start taking these input symbols from? From where? The left. So what is the first input symbol that you're going to pick up?
One, sir.
What's the next one?
One.
The next?
0.
Good. So you start from the left, you start processing it towards the right. So let's start. The initial state for this diagram is what?
Q1.
Q1. Are you the only one in class?
It's Q1, sir.
Okay, good.
Q1, sir.
Oh, great. So you have Q1. Why is it Q1? Because there's an arrow pointing at it from nowhere. That's how you identify your initial state. So you pick up what? The first one, which is what? 1. Where does 1 take you from Q1?
Q2, sir.
Q2.
It takes you to Q2. You see, you say you read 1. You follow the transition from Q1 where to Q2. So which state are you now once you have read that 1? Which state are you at present?
Q2.
Second state, Q2, sir.
Good. So you now stay at Q2. Now, this is one of the mistakes most people make. They are forgetting that they have made a transition from Q1 to Q2. When they now pick up the next one, they will now go and start from Q1. No, you're already in a new state now, which is Q2. Now, once you pick up an input symbol 1, where do you go? You remain on what? Q1. Look at the transition. Let me clean it so that you see. You see this arrow? It's pointing back to where? To Q2. See the arrow pointing back to where? Q2. So it says that once you are on Q2 and you read a 1, you remain at where? Q2. You are still on Q2 here. What's the next input symbol? 0. You move to where? Q3. So this is, you are now in state Q3. You read the last input symbol, you follow the transition from Q3 to where? Q1. So where do you stand now? You are now in Q2, which is the final state. So when we now say that you have read all the input symbol and you are now on a final state, we can have several final states. It doesn't mean that we just have one. So it means it accepts because M1 is in an accept state, Q2, at the end of the processes of the input symbols. So once you are processing and you find out that the automaton is on its final state, we say it's accepted. If it's not in the final state, we say it is rejected. So that's how you conclude. So if I give you a diagram like this and I ask you to interpret the movement, you can use this English form or you can use a mathematical notation, right? And we're going to be looking at such formalism very soon. So do you understand what this symbolizes, all these movements of reading of input symbols?
Yes, sir.
Okay.
Yes.
So moving on. So it now says this same diagram. Can somebody just look at it and tell me that if this input symbol will be accepted? Will this input symbol be accepted or rejected? Just do it mentally, quickly.
So it will be accepted.
Yes, sir. It will be accepted, sir.
Good. That means at least you see that the last input symbol either ways is 1. So if you're in Q3 or anywhere, or you're in Q1 and you receive a 1, you'll be forced to stay in Q2. That means it will be accepted. But if I tell you to now write it out formally, you know what you're supposed to do. You go write it in this form. Start from Q1, read this. So let's look at that as our second assignment. You look at all of these, then you write the processing from left to right using this automaton. Moving on. So although state diagrams are easier to grasp intuitively, we need formal definition too for two specific reasons. So some languages, some automaton can just be very nice, but there may be ambiguity. Just as I said, you are coming from your hostel and suddenly the car breaks down and you are deciding, oh, do I get a cab or do I start jogging? Okay, you say, oh, it's raining, so it's better I get a cab. So if you get to the final bus stop and it's still raining, what do? Do you remain in the cab, hoping that, oh, let the rain stop so that, or you hide under Zenith Bank so that the rain will stop? The truth is that you have not got to the venue of the lectures, right? So if we need to define steps that you need to go through in getting to the class, we make it as simple as possible. However, if complexity is going to come about, we can now define other contingencies. But you may not understand that for now. Let's go. So first, a formal definition is precise. That's why we want to define formal reasoning on it. It resolves any uncertainties about what is allowed in a finite state automata. My definition of automata for you is wake up, dress up, get a cab, get to class. That's my automaton. Now, there are other things that you need to solve by yourself in getting to the class. I am not interested in that. So if I define that automaton, get up, dress up, get to class. Anything in between resolves any ambiguity. I'm not concerned. Just get to class before 12, and that is it. I don't say, sir, somebody did his face like this, so I had to go and meet the person and ask him, are you looking at me that way? It is not in my automaton. I didn't describe it. So if you were uncertain about what finite automatons were allowed to have, if you were uncertain about whether finite automata were allowed to have zero accept states, or whether they must have exactly one transition exiting every state for each possible input symbol, you could consult the formal definition and verify that the answer is yes in both cases. This statement is very deep. Reason being that when we are moving further, you see more than 2 or 3 um, exit point, transition points coming out of just one state, going to different states. As a matter of fact, you see that some states don't even have anything going out of them. So in order to resolve any ambiguity that why is this thing not having any exit state, you must look at the formal definition. Second, a formal definition provides notation. Good notation helps you think and express your thoughts clearly on that model. Okay. So the language of a formal definition is somewhat arcane, which means is either deep, having some similarities to language of a legal document. You see, I was telling you in the first class that once judges wants to uh, get their case out, they look at the argument of both counsel, and based on the truth nature of what they have said, he pronounces his judgment. So both needs to be precise, and every details must be spelled out. A finite automaton has several parts. It has a set of states and rules for going from one state to the other. Now look at that now. We are now introducing another concept from where we have known the initial states, or we have known the final state, yes. We have known the states, yes. And we have known the movement from one state to the other. However, there are rules that we must follow in moving from state to state. So it has a set of states and rules from going from one state to the other, depending on the input symbol. So you know what the states are, you know what the transition is. So we want to define rules, a grammar that will guide our transition, and you know what input symbol is from our second lecture, from string, an input symbol, just as we have done in the previous slide. It has an input alphabet that indicates the allowed input symbol. Now, what is the input alphabet of this diagram? The input alphabet is just what? Zeros and one. That's the input alphabet. You didn't see any other thing aside from zeros and one. Okay. Where was I? So it has an input alphabet that indicates the allowed input symbol. So your input alphabet defines what is allowed as your input symbols in a string. So that means input alphabet, which is usually the summation sign, is always defined that these are the allowed symbols that can be on that string. Now it has a start state, right? You know the start state now, and it has a set of what? Accept states. When we say set, that means you can have more than one accepting state or accept states or final. Now, accept states can also be called the final states. So please take note of that. Start state or initial state, accepting state or final state, they can be used interchangeably. So the formal definition says that a finite automaton is a list of those 5 objects: set of states, input alphabet, the rules for moving, the start states, the accept state. So let's see what you know. You know the accept state, good. You know the start state, good. You know the input alphabets now, yes. And you know the sets of states. So what is the rule for moving? It is that line moving from one state to the other. But what is the rule? That's what we want to make you understand. So in mathematical language, a list of 5 elements is often called a 5 tuple. That's 5 as much. Hence, we define a finite automata to be a 5 tuple consisting of 5 parts. Now, what are those 5 parts? We use something called a transition function, right? So we're introducing another thing now called transition function. And it is the grammar or the rules from moving from one state to the other. That arrow that you are seeing is what we define a rule on it, which is called the transition function, frequently denoted by a delta to define the rules for moving. So if the finite automaton has an arrow from state X, now please pay close attention so that you don't get it complicated from here. Now, if a finite automaton has an arrow from state Q, so let me draw so that it's be easy for you to understand. You are in state X, right? To a state Y, this state Y. So if a finite automaton has an arrow from state X to state Y, do you understand what I've drawn now? From state A to state Y. Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Yes.
So I'm trying to interpret what I'm reading so that it don't look strange to you. With the input symbol 1, so this is the input symbol 1. That means that if the automaton is in a state X and it reads a 1, it then moves towards state Y. Excuse me, and we have looked at that before. So you are in state X, you read a 1, you move to, you are in state X, you read a 1, you move to Y. That is the rule. So what is now the grammar? So we can indicate the same thing with the transition function by saying that delta, now this is what you are going to be representing, going forward. So when I say it, writing in English and translating is very important. So it says delta, you are in state X, right? You receive an input symbol 1 or an input alphabet 1, then you move to where? You move to state, a new state called Y. And that's what is represented here. He said the transition function states that if you are in a state X, upon the receipt of an input function 1 or input symbol 1, you transition to state. Yeah, sorry, just a bit. All right, yeah, sorry. So I said, so you understand what this representation means now. So once you see it, you say, okay, delta x comma 1, you go to what? Y. This is the grammar defined for transition. You are in a state X. Upon the receive of an input symbol 1, you move to state Y. That's it. So this notation is a kind of mathematical shorthand. Putting all together, we arrive at a formal definition of finite automata. Now, you see this simple writing. Let's see what it represents. You see this plenty language that you are writing here. This is what you can represent it with. So look at this guy now. You just say once you are in state Q1, so say delta Q1, this is what you want to interpret this line. You read a 1. Now, where do you go to? You go to state Q2. Simple. Or you can put equals to Q2. That's the same thing. So instead of writing these long sentences, just write this and you have represented it. So you see, we are converting from notation to English and back, right? So we can now define it formally as what? A finite automaton is a 5-tuple which has Q, summation sign, delta Q naught, and F, right? So where Q is a finite set, called the state. So it has several states represented by global Q, which can be small letter Q1 to Qn. Then we have the summation sign is a finite set of alphabet that is allowed to be in the string that we're going to pick our input symbol from. So for that diagram, our finite set of alphabet is what? Zeros and one. Then we have the transition function, which is delta, that you are in a particular state. You're in a particular state and you receive any input symbol that is within that alphabet, you move to another state in the collection of states. Then Q naught, which is an element of what? Q, is the start state. How do you identify Q naught or the start state? The arrow coming from nowhere. Then F, which is also an element and is the last element of Q, is a set of accept states, right? How do you identify accept states? With double circle. Now you are a bit being baptized into finite state automata gradually. So this diagram again, what's it doing here? Let's now define this guy formally from what we have done to interpret it informally before. So it says that we can describe M1, which is this diagram, formally by writing M1 to be equals to what? Q, summation sign, delta Q1 and F, where Q is set of states. And how many states do we have here? 3, Q1, Q2, Q3. Then the alphabet allowed is was 0 and 1. Then the delta is described as this. So this is the transition function that will take us to the final state. All of this is the transition function. Then Q1 is the start state and F is Q2, which is the final state. So most of our work is going to be around the transition function going forward. All our manipulation, all our thinking will be around what? Delta, which is transition function. So please understand what our Q1 is, what our Q2 is, what is allowed alphabet within the symbol, then set of states. Then this is important for you to know the transition function too. All right. So if A is a set of all strings that machine M accepts, we say that A is a language of machine M, and write that L into open bracket M, that's close bracket, equals A. Now we say that M recognizes A, or M accepts A. Now, because the term accept has different meanings when we refer to machine accepting strings, the machine accepting and the machine accepting language. So there's a difference between a machine accepting a string and a machine accepting a language. So we prefer the term recognizes for language in order to avoid confusion. So an automaton recognizes a language and accepts a string. So a machine accepts several strings, but it always recognizes only one language. So if the machine accepts no string, it still recognizes one language, namely what? The empty string. Remember, in our previous definition, when we're doing the clean closure and the clean star, we define an empty string to be represented with what? A file or a lambda. That's what you are seeing here. Now, in our example, let A be equals to W, given that W contains at least one and an even numbers of 0 followed by what? Last one. How can you interpret this? Contains at least one, even numbers of 0, that means even, the first even number is 2, then at least 1. Simple for interpreting. Then the language that M will recognize, which is A, or equivalent, M recognizes A. Who is that individual? Who is this allow what day something? And you mute yourself or exit the class. Allow what day mo lolua. Right. Moving on. So a language recognize a string is accepted. Well, I'm sure that most of you are tired now. To myself, I think I'm tired of teaching you. So in order to wake you up, let's just quickly do a bit of a test. So, well, let's look at this together. You see, I want to emphasize that look at this guy. How many accept state does he have?
2.
Two, sir.
Good. So that means the first one we did was just a simple notation model, right? So don't think that all the time we must have just one accept state. And don't also think that we must always have one initial state. It may be different. So if you look at this now, show that the figure above accepts string A, B, AA, BB, BAB, and all of this. Okay, so maybe this will be your assignment 2. So we have looked at assignment 1. This is your assignment 2. Test each of these string to see if it's accepted. So this is how you do. You get a sheet of paper, you write your name, your matric number, you sign up and down, right? You submit latest by Thursday by 2 p.m. Physical. You submit your class rep, he gets it to the office. Okay, so just look at this and attempt to solve that. Now, so formal definition of computation. So far, we have described finite automata formally using a state diagram with a formal definition as what? A 5-tuple. The informal description is easier to grasp at first, but the formal definition is useful for making the notation precise, resolving all ambiguity that may have occurred in the informal description. Next, we do the same for finite automatons computation. We already have an informal idea of the way it computes, and we now formalize it mathematically. So we say M1, which has all of these 5 properties, be a finite automaton, and let W be W1's Wn be a string where each Wi is a member of the alphabet. That means 0 and 1. Then M accepts W if a sequence of states R0 to Rn in Q exists with 3 conditions. And what are those conditions? The first condition is 1, that there is an initial, please can you be quiet? There's an initial symbol or initial state, which is R0, which is equal to what? Q0. There is a transition function defined that once you are at R1, upon the receipt of the next input symbol, you transit to the next state for R equals 0 to N minus 1. Then there is a state called Rn, which is the final state. So condition 1 says that the machine starts in the start state. Condition 2 says that the machine goes from state to state according to transition function. Condition 3 says that the machine accepts its input if it ends in an accept state, right? So all of this is what we have been dealing with for the past few weeks. That's just what we want to introduce ourselves, this computational model, how to define the transition and how to think on it. So in the subsequent lectures, we'll learn how to move from one computational model to the other, and also how to think on those computational models. And it's important that you learn the transition function properly. Go back, look at it, understand the concept of transition function and how it can be represented in many folds. So we say that M recognizes language A if A equals to W, given that M accepts W. So a language is called a regular language if some finite automaton can recognize it. So I'm sure, okay, at least you are doing compiler construction. So you'll be seeing some of these things just crossing boundaries here and there, right? So of course, we looked at what regular language is. We looked at what grammar is. You see, what we have done in this transition function is to define a grammar to force that automaton to behave in certain ways. So if a grammar is not defined on you as a university student, you can just decide to be going to parties from semester to semester until you graduate. But an automata is defined on you by giving you a timetable that once it's 12 on Monday, you must be in class to take automata theory and computability. That is a grammar forced on you. to be able to come to class. Else, some of you will still be sleeping by now, right? So that is the crossing and exit that we have in automata theorem. Yeah, so I hope at least you understand a bit of what we have done today so far. And when the class becomes even more tedious, just go back to the beginning so that we'll be able to understand certain concepts that has been learned over a period of time. So thank you for attending the class. So it's time for you to send in your attendance. At least your attendance has improved a bit. You have 156. That means almost 100 of you are still absent from class today. Okay.